124 light-years away, there's a planet that briefly convinced a meaningful slice of the astronomy world that humanity might have just found the first real evidence of life beyond Earth. For a few months, in 2025, it wasn't a cautious footnote buried in a journal supplement. It was the lead story on major news outlets around the planet, discussed on television, debated on social media by people who had never previously followed exoplanet research, and cited by some commentators as a genuine turning point in the centuries-old search for life beyond our own world. Then, one careful reanalysis at a time, conducted by scientists who had no stake in the original claim being wrong, that evidence started coming apart in public in front of the same global audience that had just been told it might be real. This is the story of K2-18b, the biosignature that briefly electrified an entire field, and the thing James Webb's own data has since forced scientists to admit, however reluctantly, nobody involved actually wanted to admit. Before we get into it, if you're new here, this channel covers space and astronomy the way working scientists actually talk about it among themselves, without the exaggeration that usually gets layered on top once a story like this reaches the wider public. If that sounds like your kind of channel, the subscribe button is right there, and it genuinely helps this content reach more people who want the science explained straight. Beat 1. The planet and the theory. The planet at the center of this story is called K2-18b, a world first identified years ago orbiting a small, cool red dwarf star roughly 124 light-years from Earth. It's substantially larger than Earth, somewhere around 8.5 times the mass, and 2.5 times the radius, which puts it in a category planetary scientists call a sub-Neptune, a size class with no direct equivalent anywhere in our own solar system. Critically, K2-18b sits inside its star's habitable zone, the band of orbital distance where surface conditions could, in principle, allow liquid water rather than ice or steam. A specific theoretical model proposed for planets like this one gave K2-18b its real claim to fame. Some researchers classify worlds in this size and temperature range as potential Hycean planets, a term combining hydrogen and ocean, describing a hypothetical world with a thin, hydrogen-rich atmosphere sitting on top of a deep, possibly habitable global ocean. If that model actually applies to K2-18b specifically, and that if is doing a lot of work in the story, it would be exactly the kind of environment where simple microbial life, if it existed, might produce a detectable chemical signal in the atmosphere above it, one that current telescopes could actually pick up from 124 light-years away. Beat 2. The first hint. In 2023, a research team led by Cambridge astronomer Niku Madhusudan pointed James Webb's near-infrared instruments at K2-18b during a transit. The brief window when the planet passes in front of its star from Earth's perspective and starlight filters through its atmosphere on the way to Webb's detectors. Buried in that filtered light, the team reported a faint, tentative signal consistent with dimethyl sulfide, a gas that on Earth is produced almost exclusively by marine biological processes, largely phytoplankton in ocean surface waters. There is essentially no known significant abiotic source of dimethyl sulfide on Earth, which is precisely what made even a tentative detection worth taking seriously. The team was careful in how they framed it at the time. The signal was weak, sitting well below the statistical threshold scientists require before calling something a confirmed detection, and the paper described it explicitly as needing further observation. But the underlying implication, that a molecule strongly associated with biology might be present in a habitable zone planet's atmosphere, was enough to generate real, sustained excitement inside the astrobiology community, even before any headlines picked it up. Beat 3. The signal comes back stronger. The story escalated in April 2025, when the same Cambridge-led team returned with a new set of observations, this time using Webb's mid-infrared instrument, a completely different detector, covering a different range of the light spectrum than the original near-infrared study. Independent confirmation across 2 separate wavelength ranges, using 2 different instruments, is exactly the kind of evidence that's supposed to move a tentative claim toward a credible one. This time, the team reported a statistical confidence of roughly 3 sigma for the presence of dimethyl sulfide, along with a closely related molecule called dimethyl disulfide, another gas linked on Earth almost exclusively to biological activity. It's worth being precise about what 3 sigma actually means, because a lot of the public confusion in this story traces back to that number getting misunderstood. In astronomy and physics, the 3 sigma result corresponds to roughly a 1 in a few hundred chance that the observed pattern is simply random statistical noise rather than a real signal. That sounds convincing, and in a lot of contexts it would be, but the formally accepted threshold for declaring a confirmed discovery in physics and astronomy is 5 sigma, corresponding to odds closer to 1 in a few million. 3 sigma is evidence. It is not proof. The Cambridge team never claimed otherwise in the paper itself. The public conversation around the paper did not preserve that nuance. Headlines across major outlets ran with language like potential signs of life and biosignature detected, and for a stretch of weeks in the spring of 2025, K2-18b wasn't being discussed as an interesting hypothesis anymore. It was being discussed in a lot of public spaces as though the discovery had essentially already happened. Beat 4, where other teams started looking. Almost immediately after the April of 2025 paper became public, other independent research groups began doing exactly what the scientific process is supposed to encourage, pulling the same publicly archived web data and trying to reproduce the result themselves, using different analytical approaches. And that's where the story turns, and where the title of this video actually comes from. A team that included researcher Louise Wellbanks found that the original detection was highly sensitive to a specific modeling choice, namely which candidate molecules the statistical analysis was allowed to consider in the first place. When the original team's constrained model, built around a narrower list of candidate gases, was widened even slightly to include a broader, more realistic set of molecules that could plausibly exist in that kind of atmosphere, the statistical preference for dimethyl sulfide specifically weakened substantially, in some versions of the reanalysis nearly disappearing entirely. In other words, part of what looked like a signal pointing specifically toward a biosignature gas may have actually been an artifact of how narrowly the original search was framed, rather than something the data itself was strongly insisting on. A separate reanalysis effort dug into the mid-infrared data, specifically, and found that the spectrum was unusually sensitive to small, largely unavoidable quirks in how Webb's mid-infrared instrument processes light at those particular wavelengths. Different reasonable, defensible choices about how to calibrate and process that same raw data set produced meaningfully different atmospheric interpretations, not a single consistent signal that held up regardless of methodology. That's a serious problem for any claim resting on a specific molecular detection, because it suggests some of what looked like a chemical fingerprint might partly reflect how the data was processed rather than what was actually happening in the planet's atmosphere. Beat 5. The NASA study that went looking directly. The most direct test came in July 2025, when a NASA-led research team took a different approach entirely. Rather than reanalyzing one dataset with adjusted assumptions, they pulled together the full combined set of Webb observations of K2-18b, both the original near-infrared data and the newer mid-infrared data, and ran a systematic, wide search across the entire combined dataset specifically for the presence of dimethyl sulfide and related sulfur-bearing molecules. Their conclusion was two-sided and worth stating carefully rather than compressing into a single headline. On one hand, they confirmed that K2-18b genuinely does have a complex, chemically rich atmosphere, including strong evidence for water vapor and other molecules, and that it remains one of the most interesting habitable zone targets currently available to study in detail. On the other hand, when they specifically searched the full combined dataset for dimethyl sulfide, the molecule at the center of the entire biosignature story, they found no statistically robust, conclusive evidence for its presence at all. Not a weaker signal, not a smaller but still meaningful detection. No conclusive evidence, full stop, once the full dataset was searched systematically, rather than through the narrower lens of the original analysis. Beat 6. The verdict gets blunter. By January 2026, a further independent analysis from a research team at Arizona State University added what amounted to the bluntest assessment yet. Their conclusion described the original dimethyl sulfide detection as most likely a false alarm, with the statistical signal best explained by a combination of instrumental noise and known, entirely ordinary non-biological chemistry, rather than any actual biological process occurring on or above the planet. It's worth pausing on why that kind of walkback happens, because it isn't a story of anyone acting in bad faith. Dimethyl sulfide happens to absorb and emit light at wavelengths that overlap at the resolution current instruments can achieve, with several other molecules that have nothing to do with biology. Researchers specifically pointed to ethane, a simple hydrocarbon already well documented on multiple worlds inside our own solar system, including on Saturn's moon Titan, as a substance capable of producing a very similar spectral signature under the right atmospheric conditions. One astronomer working on the reanalysis put the underlying scientific principle plainly. When a known, unremarkable non-biological molecule can plausibly explain an observed pattern in the data, the standard practice is to rule that explanation out thoroughly before reaching for the exotic, biologically associated interpretation, not the other way around. In the rush surrounding the original announcement, several scientists have since suggested that ordering got compressed. Beat 7. This has happened before. It's also worth placing this story in context because K2-18b is not the first time a promising biosignature claim has generated global headlines before ultimately failing to hold up under sustained scrutiny. In 2020, a detection of phosphine gas in the atmosphere of Venus, another molecule associated on Earth primarily with biological or industrial sources, and one that generated a very similar wave of public excitement about a possible sign of life in our own solar system's backyard. Subsequent reanalyses by other teams found the original signal to be much weaker than initially reported, likely explainable by sulfur dioxide, an entirely mundane and expected component of Venus's atmosphere, rather than anything biological. The pattern across both cases is strikingly similar: an initial detection near the edge of statistical significance, a wave of public attention that outpaces the actual confidence level involved, and then a slower, less publicized process of independent reanalysis that gradually walks the claim back toward a more mundane explanation. Researchers actively working in the astrobiology field have started explicitly discussing this pattern as a systemic problem worth addressing directly, not simply a string of unrelated disappointments. Beat 8. Building better standards. The growing awareness has led to something constructive coming out of this story. Groups within the astrobiology and exoplanet research community have been working on formal, agreed-upon frameworks for what a genuine biosignature claim actually needs to survive before it gets publicly described as a discovery rather than a promising hint. Proposed frameworks generally call for signals well beyond the 3 sigma threshold, ideally approaching the 5 sigma standard used elsewhere in physics, along with independent confirmation across multiple separate observing runs, agreement across different analysis methods and instrument modes, and a systematic, explicit effort to rule out every plausible non-biological explanation before biology gets seriously considered. Researchers involved in developing these standards have been direct about why this matters beyond just scientific accuracy. Chasing headlines with premature announcements, several have argued, risks eroding public trust in the broader search for life, specifically at the moment that search is becoming more technologically capable than ever before. A public that's been told twice, first with Venus and now with K2-18b, that scientists found evidence of life only to walk it back months later, may reasonably grow skeptical of the next claim, even if that next claim turns out to be the real one. Beat 9. What comes next? None of this closes the book on K2-18b, and it's worth understanding what the next stage of investigation actually looks like, because it explains why scientists describe this as an ongoing story rather than a finished one. Webb's science team has additional transit observations of the planet scheduled across its extended mission timeline, and each new transit adds another independent slice of data that can be checked against everything gathered so far. Because K2-18b orbits its star quickly compared to a planet like Earth, transits happen relatively often, giving researchers a genuine opportunity to accumulate enough independent, high-quality observations to eventually settle the dimethyl sulfide question one way or the other, rather than relying on a small handful of transits the way the original claim did. Beyond Webb, upcoming instruments are being built with exactly this kind of problem in mind. The European Space Agency's Ariel mission, expected to launch toward the end of this decade, is specifically designed to survey the atmospheres of a large sample of exoplanets in a systematic, standardized way, which should help astronomers understand how unusual or how common atmospheres like K2-18b's actually are across similar planets. Rather than studying this one world, and large telescopes currently under construction are also expected to eventually contribute independent spectroscopic data using entirely different observing techniques than Webb's space-based instruments, adding yet another layer of cross-checking that wasn't available during the original 2023 and 2025 observations. There's also a quieter, methodological legacy to this story that's arguably more important than what happens to K2-18b specifically. The public back and forth over this planet has pushed the exoplanet research community to be considerably more explicit, in real time and in full public view, about exactly how confident a claim needs to be before it gets communicated to the wider world as a finding rather than a possibility. Several of the researchers involved in the reanalyses have said directly that future claims on this planet or any other will likely be held to a noticeably higher, more clearly defined bar, specifically because of what played out here, in front of an audience that was watching closely enough to notice when the story changed. Beat 10. How a hint became a headline. It's worth spending a moment on the mechanics of how a 3 sigma hint, explicitly described by its own authors as needing further confirmation, ended up being reported across much of the world as though the discovery had essentially already happened. Because that gap between what was actually published and what the public understood is itself part of the story. And it's a dynamic that shows up again and again in science communication, not just in astrobiology. Part of it comes down to how press materials get built around a paper like this. University press offices, working from the same underlying data as cautious researchers, often have institutional incentives to frame a result in the most compelling way that remains technically defensible, and phrases like potential biosignature or possible signs of life are accurate in a narrow technical sense while still being read by a general audience as something much closer to confirmation. Individual outlets picking up the story then compress that framing further, since a headline has far less room for statistical nuance than a press release, let alone the original paper. By the time the story had passed through several rounds of summarization, the 3 sigma caveat that had been prominently stated in the original research had, in a lot of public coverage, disappeared entirely. Some of the scientists involved in the original detection have since said publicly that they were uncomfortable with how far the framing drifted from what they'd actually reported, even as they stood behind the legitimacy of investigating the signal in the first place. That's an important original research team of overstating their own findings in the paper itself. The criticism, where it existed, was aimed much more at the media ecosystem surrounding the paper and at how difficult it apparently still is to communicate a genuinely interesting, genuinely tentative result to a general audience without it mutating into something closer to a confirmed finding somewhere between the press release and the headline. That's part of why researchers building formal biosignature standards have started talking not just about statistical thresholds, but about communication protocols too. Essentially templates for how a team should describe a tentative result publicly in a way that's harder to misread before the underlying evidence has cleared the much higher bar required to call something a confirmed discovery. Why this matters. None of this walks back interest in K2-18b as a planet worth studying. If anything, it remains one of the best characterized, most chemically interesting habitable zone worlds currently available to astronomers, and Webb is expected to keep observing it as more transit opportunities become available. What this story actually captures is something bigger than any single planet, a live, ongoing demonstration of how the scientific process is supposed to work when it's functioning correctly, even when that process is uncomfortable, slow, and occasionally embarrassing for the researchers involved. A tentative signal got published with appropriate caveats. The public conversation stripped those caveats away almost immediately. Other scientists went back to the same public data, tested it from multiple independent angles, and gradually built a clearer, more honest picture, one that happens to be less exciting than the original headline, but far more likely to actually be true. Closing. So no, James Webb didn't find aliens, and nobody currently working on this. Data believes it did. What it found, once scientists pushed hard enough on the numbers, was a reminder of how easy it is to want a signal to mean something, how much slower and less glamorous the real work of ruling out ordinary explanations actually is, and how much scrutiny even a headline-grabbing 3 sigma result has to survive, before it earns the right to be called a discovery. The search for a genuine biosignature on K2-18b or anywhere else hasn't ended. It's just continuing more carefully now, with a clearer sense of exactly how high the bar needs to be before the next headline gets to claim we finally found it. There's a version of this story that would have been more satisfying to tell, one where the original signal held up, where every independent team confirmed it, and where this video could have ended by telling you humanity had genuinely found evidence of life somewhere other than Earth. That's not the story the data actually supported, once enough people looked closely enough, and pretending otherwise wouldn't do you, or the researchers who did the hard, unglamorous work of checking any favors. What's left instead is arguably more valuable in the long run, a clear public demonstration of how science is supposed to correct itself, and a much better defined bar for the next planet, and the next tentative signal whenever it turns up. If deep dives like this into real, sourced space science are what you come here for, subscribing helps this channel a lot. Drop your take on the K2-18b story in the comments, whether you think the original team jumped the gun, or whether you think the reanalyses are being too conservative. It genuinely shapes what we cover next, and sharing this with someone who remembers the original headline is the easiest way to support the channel.